Hello, everyone. This is Ekin from Makeathon department from TUM.ai, and today we are gonna start with deep dive days. This means with business talks. I hope you had a great holiday, Easter holiday throughout the weekend, because you will need that sleep in the Makeathon weekend. So let's jump into our today's agenda. So today we will host experts from NetApp and also from Siemens Healthineers, and we will ask our questions to them about their expertise and about their topics. So what are the deep dive days? During the deep dive days, today, tomorrow, and on Thursday, we will host experts from our premium sponsors, and we will get to know them, their expertise, and we will get chance to ask our questions to them. We encourage you to do so because they are really good at their expertise, and you need to use that chance and leverage it. I will keep it short. So today I'm partially a TUM.ai member, but partially a NetApp member. I will also host this business talk with Munir. He is an AI solution architect at NetApp. We are working very closely, and he is bridging the gap between the business use cases that he encounters at NetApp with new AI techniques. So he is the person that you should talk with if you have some MLOps questions. And today's topic is also about MLOps perspective for federated learning. And I'm also working together with Munir, and I'm the mentor of the Makeathon department. So let's dive into the first talk of today. How are you doing, Munir?
Doing fine. Thank you for the lovely introduction, Ekin.
Amazing.
How's everything going?
Everything is going great. I can't be happier than today. So let's dive into our topic, and I will give the stage to you.
Thank you, Ekin. Good evening, everyone. Thanks so much for being here today. With I hope that by the end of the session, you'll feel a little bit, let's say, what's happening in the federated learning world and how we can leverage MLOps inside that aspect of the machine learning as well. So, from few years, we are witnessing a tremendous progress in the realm of AI, especially machine learning, deep learning. And the number of research papers are growing exponentially every day, every second, right? Although we didn't see the same pace when it comes to productizing the AI and creating enterprise-grade, solutions. But to serve our business demands. So at the same time, there is a good news as well. So it's not only talking about we are only doing a lot in the research, but not much happening from the productization side as well. So good news is that, as per the analysts, so AI is getting mainstream, and almost every vertical, every industry is incorporating AI in their business. So one might ask, why AI now? Because as we all know, AI is not new, right? Let's break that myth. So it was first coined in almost 1950s, right? But what happened from past few years is that first, if we remember 2012, AlexNet broke all the records when it comes to computer vision model. And then afterwards, it was end of, I would say, the dark night when it comes to AI world. And some of the things, apart from, let's say, utilizing GPUs as advanced computation capabilities for solving and training the machine learning models with the accelerated pace, also the improvement came from the data side itself. Like now we have access to larger data sets. We make it easy and possible to collect data which was not before, let's say remote sites, or you have some historic data, which was called that kind of a black hole. Data was there, but we were not able to access it properly, get the right information out of that. And of course, the storage or the data management piece improved tremendously over the time, right? It's not only compute. Now we have to feed that compute at the same pace as it's kind of crunching that amount of data. Of course, how can I forget the state-of-art models breaking the records every other month, every other year, right? Talk about BERT, then GPT, then GPT-2, then GPT-3. It just, it's just growing. So state-of-the-art model played a great role in the whole journey as well. And also the frameworks, right? So a few years back when I started, my data science journey of being a data science working in few research institutes here in Germany, I guess back in days it was few models like TensorFlow, and from the R side of the world, few libraries there as well. But nowadays there are a plethora of frameworks at our disposal, right? You have PyTorch, you have Jainer, and now I lost the count, right? So you got the idea. So a lot of things happened meanwhile from past a decade, I would say, that contributed towards this journey. And that's the reason we see slowly that industries are incorporating these projects, not just POCs happening in some garage, but really taking these models out, integrating within their applications, or creating new applications that were not possible before. But as they say, grass is not always greener on the other side. Let me share this insight with you as well. As for venture beats, like 87% of the projects, AI projects, never see the daylight. So we still witness that most of the AI projects, just die in the POC stage only. And one of the main reasons for that is the data mobility and constraint associated with it. Like in Europe, we all are aware of GDPR and other regulations in place. Sometimes we have data, we have enough data at our disposal, but we are not able to leverage. Let's say one of the researchers or data scientists are sitting in India, right? And the data is in Europe, and one of our business units are in US, right? This is the advanced world. Like we have teams all across working closely with each other. And one of the problems is that data scientists in India is not able to access the data that's in the Europe because of the regulations, and sometimes the technology. So forget about sending petabyte amount of data all across the globe and thinking we'll finish this project in a stipulated time, let's say in 6 months, in 8 months. It might take months just to transfer that amount of data. And being at NetApp, right? So I have witnessed that challenge, right? It's not possible to send humongous amounts of data here and there, considering the fact that security, you had to think about the security, as well as the data can be acquired from edge devices, or we might have the data already available in our data centers, historic data like financial data, healthcare images that we have acquired over the decades. We might have historic data in our data centers, but in some cases we might want to leverage cloud for processing the data and archiving for auditing, right? The data footprint can result in siloed environment, and that can cause issues with leveraging it for our AI training and deployments. So, if you think about it, we need a data fabric that connects the dots and provides us a smooth and secure means of tapping into the plethora of data whenever and wherever needed. And it should not be that data scientists should need to manage the security, confidentiality, privacy of the data, and other aspects, right? As their core focus and most of their time should be utilized to bring intelligence to machines and improve the model performance with time. So what exactly, I talked a lot about data, I talked a lot about what's happening, but what exactly a successful project look like, right? And how do we start creating an enterprise grade AI solution? So it's not new, like, from software engineering principle, like software 1.0 or the traditional software. We also have some structure in place, right? We started with the waterfall model, then we jumped into agile methodologies and all of the methodologies that are in place, hybrid as well. So AI is not completely different from that perspective. But one thing that mostly organizations overlook is that we are not just talking about the code. We are not just talking about the configurations. But here, the important point is that the code, as well as the data, should be mapped together, right? And we should think from that aspect. So our thinking should be, hey, data is this. Now we have to think about how do we ideate it? Like ideation means that what are you trying to solve? And then to create some kind of POCs around it. Validate before you go and scale up your whole training process and deployment process. Validate your results. And when I say validate, right? So coming from the data science world as well, I used to focus on accuracies. I used to focus on ROCs. I used to focus on AUCs and all those metrics. But for the business, that means nothing, right? We have to mention, or we had to explain, if my accuracy is 90%, what does that mean for the business side of the world, right? And interpret the results, right? Because usually people think that machine learning is a black box. You feed something in and you get something out. We don't have any control. Or how do we explain that to our business units? Or how do we explain that to our customers? Why my model is behaving the way it's behaving? That's important. And finally, deploy that in the production servers, right? I'm going to go in detail in each and every point. It was just a quick walkthrough. Now, starting from the ideation phase. So we need to first of all define the success criteria, and also make sure that if you are looking to use AI, machine learning, or deep learning to solve that particular problem, does it make sense? Let me give you an example. Think about, let's say we are discussing that, what, our algorithm should tell us whether the number is even or not, or even or odd, right? So do you think that we should use machine learning, deep learning for that, and feed all the even numbers, feed all the odd numbers, and label that? That's not a good idea, because we have a deterministic solution for that, like modulus, right? Division, and that's it. Why do we reinvent the wheel and bring some probabilistic approach, which might not be good and favorable for our business? So that's important. Like look for whether machine learning is needed or not, then start your journey. And once you do so, have some success criteria in mind. Let's say you define the matrix, for example, again, accuracy. Talk with the business unit. What does that mean for them? And let me again, kind of walk you through one of the experiences before the COVID. Let's say good old days. I visited one of the conferences, AI for Finance, and after my talk, one of the subject matter experts from the fintech industry came to me and he told me that, what, I'm proposing my upper management that we are having enough data, and I want to use that to predict customer churn. And I had a good hunch that we'll get almost 80-90% of accuracy, because I tested it on a small amount of data. But I want to do it in scale. That means I need resources. I need the support of upper management later on to roll it out as well. And when I mentioned to them, hey, you know what, I'm confident that it's going to give us 80-90% accuracy. And the upper management was like, forget about it. Until and unless you don't give us 99.9999% accuracy, not going to invest, not going to spend time on it. Right? Other than defining the accuracy that should have been, what, guys, within the 3 months, I make sure that the customer's churn or the customers leaving us is going to decrease by, let's say, 20%, 30%. That's what they care about. And that's what is the responsibility of data scientists as well, to map it, to map the machine learning world to the business world and provide the insights that these folks are looking for. And sometimes in our industries, we don't have enough, let's say, data scientists. We don't have any, right? And sometimes we don't have subject matter experts. When I say subject matter experts, let's say talk about medical imaging, which is going to be the main topic for today's discussion. In medical imaging, the subject matter experts can be doctors, radiologists. For them, the data is, they play with it every day. So they know in and out about the problem. And on the other side, they need data scientists to automate, to augment the intelligence. So they have to work closely with each other, and they have to understand each other's terminology. And they have to also make sure that the problem they're solving makes sense, right, from both sides of the world. And sometimes project fails here because subject matter experts talk different language, data scientists are focusing on something else, and at the end, data scientists provide some model which is completely out of the scope. So they need to be in sync. And afterwards, as we mentioned, like the data itself, right? Because without data, forget about machine learning. Whatever you feed in to the machine or to this model, it's going to learn out of that. And not only about the quantity we are focusing, but also the quality. So quality as well as quantity is real important. And then afterwards, accessing it. I mentioned earlier in previous slides that data can be scattered, can be on edge, or in your data centers, or sometimes in the cloud. Now, how do we make sure that we can access that properly, considering all the constraints, security, confidentiality, and all that? And whenever data scientists or subject matter experts need that, they should not be having any hassle or any problem. Let's say they want to start with some ABC public cloud vendor. Tomorrow they want to move to XYZ. So they should not worry about learning those technologies, learning those new skills. For them, they should focus on their task. That's important. And here some of the challenges are availability. Do you have that data available whenever you need it? And have you kind of integrated some kind of mechanism that provides compliance? And today, let's say we are starting with small. We have hundreds of 100 patient data. But tomorrow we can scale that to thousands. And how is our whole let's say infrastructure in place are going to cope up with that? And one of the challenges that I have seen in this realm is that we usually start with buying, let's say, small workstations and industries as well. And later on, what we do is we throw them out and we get a new rig where all the folks can access it and on-demand basis. So we should have that future-proof plan in our heads before, because later on, the investment is gone, right? A business needs some outcomes. They need return on investment, and time is of utmost importance for them. And finally, the good part, that is building our models, right? Working on our experimentations. And the experiment, like no data scientist in this world can tell you, you know what, if you give me this much of data with this quality of the data, I'll give you 95 or 99% of the accuracy or all of the metrics that are there. Because it's all about experimentation, right? We don't know until unless we try it out. And whenever I discuss this experimentation, it just reminds me of my school days. In the chemistry lab, we used to do experiments like mixing different chemicals, and at the end we get some compound, right? Same is happening here. Like we have a data, so we'll, let's say, fine tune the data, kind of curate it in such a fashion that can be understood by our models at the end of the day. And at the same time, we might try different models because there is no silver bullet that's going to solve all our issues. So we need to try different models out. And we need to track them. Let's say some model that we trained 10 days back was performing better than what we are having right now, trained on a different algorithm, trained on a different data set, or different process data set. All right. So we need to track that as well. If needed, we should be able to go back. And also, we should be able to scale that. Scaling means, let's say, again, if you are growing with the data over the period of time, and today you're training that on one GPU, and tomorrow you want to use a number of GPUs that is available at your disposal in the compute farm. So there should not be a problem doing that, like doing distributed training at scale. So usually data scientists have to focus on fine-tuning, let's say, their models, fine-tuning, let's say, Harvard and this and that, fine-tuning networking, which should not be their focus, right? And also the collaboration. When you want to share your models with your fellow colleagues, let's say in big setups, you have multiple data scientists working together with data engineers, with ML engineers. So there should be a proper collaboration in place rather than, Aiken, I'm done with the data processing. Now you can start the training. I'm writing mail to Aiken and Aiken is writing me back. Where is that process data that you mentioned earlier, right? And then Aiken is done with the model training and some machine learning engineer wants to use that. And Aiken is writing, I trained and this is the best model. And how can I find which is the best model? Have you tracked that? Are you going to provide me some kind of matrix to that, like, select this or that? So the collaboration is important as well. So, and we overlook it again. I'm just stressing that point. We overlook it when we start POCs. We are happy with the notebooks, Jupyter notebooks. But later, how do you productize that? That's the challenge, right? Can you take the code snippet and somehow integrate that in the production? Or you're just going to take the model that you have trained and create some Flask application, integrate it over there, and voila, it's working because APIs. But have you thought about what's going to happen meanwhile if you're updating your models? How do you deploy that continuously? Because machine learning is not just one time you train your model, your job is done, right? Data can drift over the time. Business logic can change over the time, right? So we need to take care of those changes as we proceed. And the good thing is that after you have trained your model, let's say, again, medical imaging, let's say you trained your model today, let's say with ABC patient. And that ABC patient is coming to us after a year. And as per GDPR, he and she is having right to tell us, you should not use my data anymore. Now, how do we make sure that we didn't use her data or his data at first place while training our models? Let's say we use that data only for testing. So that information is not incorporated inside our model training, and we are fine with that. So we are not using any of her or his information. But we need to have some kind of tracking mechanism, some data lineage in place, right? Some provenance in place so that we can roll back in the good old state, or when we trained our models with the application, with the code that we have used and the configuration, right? All amalgamated together. And that's important. Like call it a machine learning versioning. Like we are having that for the code. Like you use Git, you use GitHub, Bitbucket, or GitLab. Similarly, we need to have something for the machine learning as well. Not just the code again. It should version the data itself so that we have the possibility of time travel. We go back into the time and exactly figure out what data was used. And it also helps to understand who was responsible for that particular, let's say, training experiment, right? Auditability as well. And model insights and behavior. Like there are a lot of technologies and tools out there that are helping in this direction. Let's say sharp algorithm that you can use at least to figure out what features are important and what features are triggering particular behavior or the particular outcome, which is going to internally help in our business objectives. And finally, we are ready for the production, right? Now we can deploy our models into production. And deployment, you have to think about, again, few things. For example, if I am deploying my model into public cloud ABC, that might create a problem for me that lock-in is there. That means tomorrow, if I want to move from ABC cloud to XYZ, how easy it's going to be for me, or I'm just stuck. I cannot do that, right? And if you start training in the cloud, then the data gravity might be the problem. Tomorrow, if you want to move that out, you have to think about egress cost, right? So forget about doing your training. First, you need to figure out these problems. And that's important. And the documentation, I guess, usually when we say documentation in machine learning, deep learning world, we only talk about having, again, the Jupyter notebooks, writing fancy comments, writing the visualization. That is pretty cool. But in production, that's not going to be there, right? So we need to have some mechanism in place where you have to have a proper this documentation. All the hyperparameters that you're using, data sets that you're using. You might use multiple data sets in mix. So you have to track that. And again, team members that are working on that particular project. Everything should be maintained over there. And in production, let's say you have some surge or you have a lot of customers visiting your site in some period of time. Let's say Amazon, during Christmas time, a lot of customers are visiting. So at that time, it's a peak, right? So we need to serve all the customers. But rest of the year, let's say there are just 25% of the whole users accessing that. So we need to scale up, scale down based on demand. And also when we roll new models, let's say during the test time, they are behaving amazing. They are giving us great results. But let's say in the real world, we realize that these models are not performing as much as better as the previous ones. So we should be able to easily roll back to the good old state from the model perspective as well. I was talking a lot about, let's say, data as well as model. And there is something we need to also focus on. And that is whether we are focusing on the model itself, or we need to consider data as well. On the left side, you see model centric, where we are trying to improve the model, keeping the data as such, right? Different state of the art algorithms, hyperparameter fine tuning, whether it's learning curve, it's batch size, and all that stuff. But on the right side, you might want to think about your data itself, right? You might want to improve your data. And when I say improve your data, let's say you already have some data set and you don't have, you're not getting new data set as we speak, but you can augment it. You can create synthetic data, right? Considering the whole data distribution. Or sometimes you might have to get it from others, right? In your organization, or you might have to go for the outsourcing that problem. So data-centric approach should be part of the strategy as well, rather than only focusing on the model centric. And one example is, let's say some state of the art models are better, let's say by 0.001%, right? In the paper, it's amazing because we want to show that in our papers, but for the business, is it worth, or we need to focus our shift a little towards the data as well. And my colleague Ekin is going to mention this in detail. So Ekin, stage is all yours.
Thank you very much, Münir, for the insights, also to the steps. So I will first start with model-centric AI. Most of you have already probably used model-centric AI at work or in your project or university. So here is the focus. Here the focus is on changing the model, or in other words, code to improve performance. So you have a data set, available data set on premise or on cloud, it doesn't matter. But you are changing the architecture of your customized model in order to generalize that data set at its best. So select the best model architecture, which captures and generalizes your data set best. And this is the main idea actually of model-centric approach. And right now, the majority of AI applications are model-centric, also the research. So in the next slide, you will see a very familiar face. It was like really teasing. Andrew Ng, of course. So most of you probably started your ML path with one of his amazing Coursera lecture series. So what he underlined recently is the fact that most of the AI projects or researchers are focused on the model itself, and we are not trying to optimize the data at all. So that means most of the projects are lacking the consistency of data. And he brings up the importance of improving the data in a systematic manner. But what is the systematic manner in that sense? So we first train the data as usual. We first train the model, sorry, as usual. We identify the types of data on which our model performs poorly, and we get more data. It might be via data augmentation, synthetic data generation, or collecting data, it doesn't matter. And we do that for the labels that seem to be ambiguous by the model. And we collect those feedbacks about the labels and the data in a circular way. So we do that again and again and again, which comes up to MLOps actually, and Munir will also talk about it a little bit further. So life is so easy right now, right? We can just do that again and again and again. We have data, but in the next slide, we will see that it's not that easy. It's in order to get a better generalization, we need to gather a lot of data all over the globe, maybe from the branches of different healthcare institutes from all over the globe again, branches of banks maybe. So there are different regulations, data protection regulations in those countries, such as GDPR in Europe. And that makes our life not that easy. So even if we can anonymize the data itself, it's still not that secure, or it's not that secure to use it at all. As an example, I can give the Netflix prize that happened in 2006. So Netflix announced a challenge to make their recommendation system better, and they offered $1 million, actually good price, whoever improves their recommendation system by 10%. And for that, they published a data set with anonymous movie ratings of thousands of subscribers, but they didn't publish any names, just the movie ratings. And even if the data set was anonymized, the researchers proved that as an attacker, it's actually very possible to identify a subscriber in the Netflix data set if we know about a couple of movie ratings of this specific subscriber on IMDb. And IMDb is open to everyone, actually, so you have this access. So how can we solve this issue? In the next slide, we will talk about federated learning, which is introduced by Google after these raising concerns of data privacy. Federated learning allows training models collaboratively, but without sharing any data with third parties. So in this way, we bring the model to data and the computation also to data instead of gathering data from people, like also from you. That's also happening in your cell phones, actually. So what is federated learning, how it's working? We have a central server here. The central server holds a global model with initial model parameters. And the participants, in this case, that's you, the owner of the phones, hold your own local data sets. And we thought you don't want to share your data with anyone else. And as first step, the central server sends the initial model to every cell phone or like every participant, and the participants which hold the local data on premise or on cloud, doesn't matter, extracts information from its local data with training the model, and that's sent to central server in the next slide again for aggregation. So the central model aggregates those parameters, the updated parameters, and sends the new updated, brand new model to the participants for the next rounds. And this goes again and again until the model converges. So it's a really cool technique if you don't want to share the data. Still has limitations. We will talk about that later on. So this is how the federated learning looks as a rough concept. And now I will hand over to Münir again for the business aspect of federated learning and the use cases of federated learning from different domains.
Great, thank you again. So it looks cool, right? The federated learning. That means you don't have to leave your premises, or your data don't have to see the other premises if this let's say regulations don't allow it or the technology don't allow it, right? And the business side, right? We from the business side, when we talk about any project, any let's say application, we need to have some kind of backing, and federated learning is allowing us to leverage the data that was not possible before. One of the let's say analysts like researchandmarkets.com. This is one of the snippets from the report that they publish, right? And it's evident, like from 2023, 117 million to 201 million by 2028. So the market is huge. And when we see the market is there, that means people are investing and people are seeing some outcome out of the federated learning as well. And various factors, such as the potential to enable companies to leverage a shared ML model collaboratively by keeping the data on devices, and the capability to enable predictive features on smart devices without impacting users' experience or leaking their private information, right? So looks good, right? But how and where do we start exploring federated learning, right? That's important. So, for proof of concepts and experimentation, open source frameworks are often sufficient. And some of the most important frameworks out there include, like if you want to try it out, right? Include FATE, that's Federated AI Technology Enabler. It's an open source project. As I mentioned, I'm going to focus only on open source projects that aim to support a secure and federated AI ecosystem. It's having a lot of components under the hood. Like if you are familiar with TensorFlow, you can use it, PyTorch, as well as Spark. Let's say if you're using some kind of Spark processing under the hood before you start training, you can use that as well. And they're also having their own distributed framework, which is called Eggroll. And it's pretty easy to use if you're familiar with TensorFlow and PyTorch and things like that. You don't need to learn a lot under the hood. And there is also one from the Google, which is TensorFlow Federated. It's a Python 3 open source framework. And the main motivation, like why Google was working on this particular TensorFlow Federated framework, was to implement mobile keyboard predictions and on-device search, right? So we are using our mobile keyboards, we get some recommendations. So they use federated learning for that. So almost all of us are kind of using federated learning, or kind of being exposed to federated learning use cases on every day. And PySwift is one more, which incorporates one more thing, that is differential privacy. We'll discuss that later. As I can mention, like sometimes it's not enough. Like one example was Netflix. It's not enough. If you anonymize your data, still attackers can get the personal information out of that anonymized data. Not, I mean, forget about if you're sharing. Sometimes it happens with the models itself. Like you trained your models, people can still get the personal information out of that trained model regarding particular patient, regarding particular person. So they are incorporating the differential privacy as well and encrypting the computation. So this would so with the Swift, what is missing is that you cannot work on real data science problems. It's just a small, let's say, dummy setup. But if you want to involve communication across networks, so you need to have PyGrid under the hood. So PyGrid connects that dots when it comes to the communication. NVIDIA is also having one of the frameworks, which is called FLAIR, Federated Learning Application Runtime Environment. And this has been used in many applications, like NVIDIA is having Clara for medical imaging. Later on, we'll discuss one of the applications where NVIDIA Clara was used. Again, you can use existing frameworks, but there's PyTorch, TensorFlow, and others. And there is one more from Intel, which is called Open Federated Learning Framework. Let's say if you want to use CPUs and train it over there, so OpenFL is the good choice. Again, support for all the famous, all the good known machine learning frameworks, TensorFlow, PyTorch, and others. So if you want, you can get started. I mean, these are all open source frameworks, and the data set doesn't matter. Whatever data set you want to use, you can try it on any data set and mimic the behavior of the real world federated learning environment. Now, I want to discuss some of the use cases, right? Like where can we use? Like I can mention in detail the whole federated learning setup. But from the business side, again, we want to map it to the real world use cases. Let's talk about the fintech and the insurance. In fintech and insurance world, there is a constant growth in the data protection laws, and this allows consumers and business to trust each other to keep the data safe and secure. I mean, that's why the regulations are in place. It's not always a bad thing, but that can sometimes hinder our innovation, right? So with traditional machine learning, business dependent on fintech face several issues, right? These includes getting clearance and lawful consent, as well as preservation of the data. And sometimes we just need to archive the data just to prove to the auditing team that it was not misused, right? And here, federated learning provides a simple solution. That is by keeping the data local and using data for training on different sites. For example, insurance companies have a considerable amount of data from health insurance to car to mobile to business assets. And their insured may associate with various other companies. Not within the organization, you can use federated learning, but within different companies, you can kind of collaborate because you're not sharing the data, you're not sharing the real asset, only the models at the end of the day. From the automotive vertical, right? So autonomous vertical is getting, let's say, day by day more, it's evolving. I'm not just talking about level 4 the cars are running on their own on roads, but also the whole smart city setup, right? So federated learning can provide better and safer self-driving car experience, and with real-time feedbacks. Autonomous vehicle needs these insights for responding to the new situations, like real-time information about the traffics and roads, real-time decision making, and continual learning while we proceed. Because you cannot simulate the whole infinite possibilities out there, and that's where you need to learn continuously. And you cannot send all the data. Let's say as a customer, I don't want to share my personal information, like where I'm going every day, using my car and things like that. So while as if you want to improve that customer's experience, why don't we use the federated learning, right? In the healthcare, like sharing critical patient information becomes more challenging with strict regulations like HIPAA in place. Not just GDPR. Now we are talking about HIPAA compliance, and there are other compliance as well. This is where federated learning comes into place as well. Like participating institutes train the same algorithm on their in-house data pool, and these institutes could enjoy these trained algorithms. It could allow them to access and also work around various regulations. This also opens up a pool of data from which they could learn. Let's say one research institute on healthcare is situated in Germany, and one is situated in London, one is situated in Boston, US. They can share that insight without leaking the information of the patients, right? And my colleague Ekin is going to walk us through how we use federated learning within healthcare, especially in medical imaging. Again, stage is all yours.
Thank you very much, Munir. So let's dive into an example again. First of all, I want to thank one of our AI specialists, Jack Watts, for sharing this animation with me. So since one of our tracks is MedTech, and Munir and I are also really interested in MedTech and healthcare applications in federated learning, we will go over the medical use case. Let's see, we have 7 hospitals here, and 7 hospitals want to detect neurologic disease from MRIs and or CT scans, whatever it is, and they are not in the same country. And even if they are in the same country, they just don't want to share the data, because as a patient, I don't want to share my medical data. Why would I share it with third parties? I don't know what they're gonna do. It's just personal data, and it's called sensitive data also. So I don't want to share it. The hospitals are also not willing to share that. So what we do is we gather all of the MRIs and CT images. Like, we're not gathering it, but like locally, they gather all of the MRI and CT images. And our hospital, our central hospital, the amazing one, the orange one on the left side, is sending a model to those hospitals so that they can start the training. So we don't want any kinds of data from those hospitals. We just send the initial model with the parameters, initial parameters, and let them train till mornings. We don't care. Then at some point, we will want the updates, and with those updated models, we will aggregate those models, and we will receive a new global model with the updated parameters. So what does that mean? It means that all of the hospitals contributed to that model, and we extracted the knowledge from each of those hospitals. And right now we have a global model, and we didn't even touch the data. We don't care if one hospital is in Germany or if the other one is in Boston. We don't care. We don't want to check out the GDPR. We don't want to check out other protocols in different countries. We just want to train the model, and that's how it's done with federated learning. As we said, there are still limitations, but with federated learning, we are able to train the model without sharing the data on millions of patients. That might also increase depending on your system and depending on the data that the other hospitals have. So this is an amazing tool that it's still open to the research, and I will hand over to Munir to mention about the MLOps part of the story. So the stage is again yours, Munir.
Thank you. Federated learning with MLOps, we can call it as enterprise federated learning. As I mentioned earlier, there are open source frameworks, and we discussed some of them. But when it comes to really using it in the real world, we need to think about a lot of things, right? In professional and productive federated learning scenarios, people face many challenges and many complexities. And I can highlight that this is still growing field, so we don't have, let's say, great solutions out there that work out of box. And there is a big difference between a student who is setting up a federated learning architecture for a university project, and if you are implementing it for a use case with multiple partners in the manufacturing, pharmaceutical, healthcare, automotive vertical. Like, one small mistake can be disastrous, and we are talking about lives, right? And we had to be critical about those things. So to operate an open source solution in a business context, you need a full team of developers, engineers, data scientists to build and maintain it. So fleet of guys out there. And as it lies, within federated learning for use in collaboration with partners, legal, contractual frameworks must be set up to secure compliance, privacy, as well as the intellectual property. Because at the end, intellectual property is here, the model itself that you're sharing from one side to other side, and then you're creating a global model. And when you're creating a global model out of different models that were trained on different sites, one thing is sure and one thing is certain, that we have to have some kind of regulation in place. Like, who does that now global model belong to, right? Is it the central site or is it the all the there? So they should be having some kind of agreement in place. And this is from the, let's say, legal perspective. But as I mentioned, there are technology wise problems as well, and that's where MLOps shine, right? So we are trying to automate the process as much as possible, which is going to bring us time saving. Think about when you write your code, so it can be containerized and automatically it can kickstart the training process, rather than you need to submit the job, you need to wait, what's happening to my training code, loss is decreasing, accuracy is increasing all the time. So we can automate that to a larger extent, which allows us to collaborate. Let's say you have 10 GPUs. And in good old days, during my university days, what I used to do, or what we used to do, is that we used to have an Excel sheet and mark, hey, today Munir is going to use the GPU from 10 a.m. till 7 p.m., right? And then afterwards, some other person is going to start the training. Because, hey, we all have this deadline for our thesis. We all have deadline for the papers. So we need to share it like that. But in the real world, it's not going to work like that. So automatically providing the resource based on demand, which allows us to have an efficient workflow, right? Once training is done, take the best model, automatically deploy that in the production world, and automate in the federated learning world. Let's say on different sites, model is being updated on the local data set, automate that process and send that back to the central server. Once all the models are back, now we need to sync. We need to kind of take the average of all the models or whatever methodology we will be using to combine all the insights together. That can be automated. And at the same time, when you automate it and bring MLOps into picture, you are sure that it's aligned with the business objectives. So we are not drifting from the business objectives, because that is the focus. And then you're solving some problem. You need to be aware where we are going with that scenario. Let's say in the federated learning, we have the same problem as I can mention, some MRI images and CT scans. And when we start our experimentation, we were mostly focusing on MRI scans for cancer prediction, right? And we did a good job. Our models are performing well. We did, we were working on segmentation. But over the period of time, what we realize is that our data scientists are spending more time, getting that model from one side to another other side, and our business objective were focusing on segmentation rather than managing that communication on the different sides. So that's where the MLOps comes into picture as well, and have that business alignment in picture. Now, one of the use cases, like the real world use cases, is from King's College London in collaboration with NVIDIA and Okin. NetApp played a role there as well. And what they did is they had different hospitals, like St. Mary Hospital in collaboration with King's College London. And as Aiken mentioned earlier, the challenge was that you cannot get patient data out of that particular clinic and get that to the King's College London Research Institute where they can train it. So they leverage the federated learning concept, the same fashion. Do not take out the data from the clinics, and we will use the central server at the King's College London, and we'll send the global model to all the local sites. You update those models with the data that's available there, send that back to the King's College London. We will kind of collaborate all the intelligence in one model, global model, and send that back to the different sites. And they submitted a paper as well, and they used Brad's 2018 data set for MRI scans from 285 patients with brain tumors. And in that research paper, they also showed that the accuracy was very comparable when it comes to if you consolidate all the data at one single place and train it on that. Because someone might ask, what, if you're training your model, let's say at the main site, let's say King's College London site, using, let's say, 10 images first, just to warm up the model, kind of update the parameters, and you're sending that to the different sites, there might be an issue with the data itself, like data is going to change and something is going to happen in between. So they compared, that's why they compared if the data is in one location or if the data is scattered all across. So there are real world applications as we speak, but there is a lot to do. As I can mention earlier, we have some challenge as well, and that's where we need you, makers out there to come up with the concepts, to come up with different solutions to those problems. And NetApp, we are playing a huge role when it comes to whole data mobility, whether this is the edge side, whether this is the data center, your core, or outside. So our fleet of products and solutions kind of try to bridge that gap. As I mentioned at the very beginning, in few slides, the data fabric is needed. So that's where we help our customers from our years of experience from the data management side. Whether they need intelligence on the edge side, they need to power their training in the core, right? Or they need to accelerate their journey from the cloud side without learning all the cloud vendors out there, what they are doing. Or if they move from core to cloud, learning different jargons or other way around. So no lock-in should be there. And the security, we touched that multiple times. I guess that was one of the reasons that federated learning came into picture. Security plus the technology problem, sharing the data all across the globe. And that's what we are trying to do here, from edge, core, as well as cloud. Yep, that was it from our side. So again, some questions. I mean, I have some questions for you, Aiken, and I guess you mentioned a number of times during the session that privacy. Like, can you just walk us through a little about that? Like how federated learning is helping to preserve the privacy, or is it at all, right? we might be leaking some information without having the knowledge about that.
Yes, so it's definitely not privacy preserving, and this is actually also an open discussion in research area. So federated learning still needs privacy preserving, privacy enhancing techniques on top of this architecture. We didn't go into detail to keep it short, but for example, as you mentioned, differential privacy, like adding some noise to the model parameters before sending it, so that the individuals are not are covered with the noise, and the attackers can't distinguish between individuals if you add only one person to the data set. Or we have secure multi-party computation, SMPC. That's also a way to enhance privacy. But they also bring some downsides, of course, with the new techniques. For example, differential privacy is adding a lot of noise to the model parameters, and this decreases the model accuracy or the metrics that you are using. And the other ones have some network communication issues or computation issues, for example, homomorphic encryption. So they have like pluses and minuses at the same time, and it's still open to research how we can optimize these trade-offs. It's really exciting, to be honest, to see what everyone is coming up with. But yeah, I think we are the people who will come up with new techniques to get over those downsides. So if you feel inspired, please feel free to read some articles and just go there and try to check it out. So yeah, that's how it looks. Promising federated learning, because we are not sharing any data, but we still have downsides, unfortunately. Then we are waiting for your questions. During this time, I will ask another question to Munir. So we talked about servers and, like, for example, central server. What happens if the central server is down, for example, and we need to update the model? We have nodes and the master node is down, let's say. What do you think?
Yeah, absolutely. So that's a great question. So basic flavor that we discussed today. So central server is the single point of failure. If that server goes down, federated learning, there is no communication happening between different nodes. You cannot update your models because the one server that is responsible for all of that is no more there. But there are different remedies available, like you have blockchain federated learning, where there is not a single, let's say, central server that changes over the time. And blockchain is being used to have that kind of ledger mechanism. So you have all the transactional information over there, like where is my global model right now, who is responsible to update that, and they can change the rules as we proceed. But as I mentioned, it's pretty new field, and a lot of things needs to be addressed there as well. And on the other side, we also have some similar approach, but different from the federated. It's called swarm learning, where they use a completely different methodology. for attaining the similar kind of results that we discussed today. Like, your data is not going to leave the sites, but still you can update your models at a global level. And that also is using the blockchain. So now you can see again, it's not just one technology that's there, like federated learning, amalgamation with the blockchain. So a lot of things and a lot of technologies that we can explore and kind of make some context out of that.
Amazing,
Uh,
amazing.
and Aiken, you mentioned earlier that when we were discussing the privacy, that we have some approach, and sometimes the computation is a bottleneck,
Yeah.
right? And apart from privacy in general, do you think that we have the issue with the computation capabilities on devices side?
Yes, exactly. For example, let's say one hospital. I'm talking about medtech use case. One hospital don't have the computation power to train the model. That might be the case. I can't even train some models on my local PC. Like, how can we expect a hospital to have a GPU or something like that? Or edge devices, they might have lack of Wi-Fi or network connection in general. So these things also needs to be considered depending on the use case, and that's another challenge again, to make the system consistent, even if there are some connections that we can't just handle from the central server. So that's another challenge, definitely. And I started to receive a lot of questions for you, Miner.
Amazing.
The next question, how do you ensure to get the right quality data in huge company structures with multiple systems? What are strategies to improve the data in a data-centric model? So I think...
Yeah, I mean,
Yeah, go ahead.
I can go. So there is no silver bullet solution, as I was discussing earlier. It's really depending on the use case, what we are trying to solve. And let's say before we start the training, almost half of the time goes to understanding the data itself and cleaning that in a fashion so that it makes sense from the business side of the world. There are different technologies, there are different techniques that can help us. Like, you can use different analysis approach that we have over there. Right? Sometimes visualization helps us as well. But when you have billions of data points, it gets tricky to use that kind of visualizations. And then the distributed frameworks like Spark and very similar technology stacks can help us to crunch large amounts of data. Like, from cloud providers, you have BigQuery kind of engines that can help us to process lots of data. You can create aggregates out of those data sets to come to some conclusion. But again, it's highly dependent on the use case and the problem that you're trying to solve. And I guess that's why data engineers are getting paid for, right?
Yes, exactly. And the second question is about the topic that we just mentioned. Actually, someone is asking, I imagine that many hospitals lack the necessary resources for intensive training. On point, yes. Does this mean you provide the hospitals with the GPUs to perform the federated learning, or do you just make with the existing infrastructure? There are some different protocols, to be honest, in federated learning. We didn't go into detail again, but we can, of course, provide GPUs to hospitals just to train models. So it's all about the algorithm, like which server is there, which is available right now, and just gathering those, or like randomly choosing. So that's mostly like that. Do you have any points to add, Winner?
Well, it's spot on, Aiken. So unfortunately, I'm not getting that much paid that I'll just distribute GPUs to every hospital. But yeah, apart from jokes, so we have different techniques, as I can mention one of them. And you can also use, let's say, if you're using, usually we use floating point 32 to store those weights as a variable. But you can use int8 as well, just to reduce that from the computational perspective. That's going to be having impact on the performance, definitely. But at least you are able to train on the local sites. For example, on your mobile phones, as I was giving example of the Google, that's where they came up with the TensorFlow federated learning concept, or the framework, is they're training those models on your mobile devices only. So you don't have enough computational power over there. And most of the time you are using the mobile phone. So you're not, at that point in time, automatically algorithm should give you the more computational power rather than for training the models. So there are some, let's say, available process and mechanisms that can handle that to some extent. But yeah, there is always a trade-off.
Yeah, exactly. And another question is about good labeling. How can you ensure good labeling quality with federated learning? Millions of people with the same question.
Yeah. Again, yeah, it might be, let's say, if we get it right. So from the good labeling, you mean that we are not having some data which is, let's say, accidentally annotated. Let's say cat is annotated dog, dog is annotated cat, or vice versa. So if that is the case on, let's say, we are having this kind of data in the federated learning fashion, of course, on different sites, then there is a problem. It's called client-side model tampering. Our client sides are having data which is not exactly as it's expected, because you cannot govern every site, whatever they are using from the training side. We don't have any insight on that, because that's where federated learning comes into picture, managing the privacy. So if that happens, so that's why the parties that are participating in this kind of setup, they should be, authenticated, and they should be having some kind of authorization mechanism in place. Otherwise, it's gonna create problems rather than solving. So yeah, that's the thing. But in generally speaking, if you're talking about good label data, you need labelers, right? And machine learning, unsupervised or semi-supervised learning, can help to some extent. But at the end, humans should be in the loop to make the data much better.
Hope to see some more improvements in self-supervised learning.
Likewise.
Okay, then I'm moving to the next question. Hospitals likely have different ways to structure their data. How do you make sure that the data at all the hospitals is in the same format? For example, do you have a software engineer on site to create the data pre-processing pipeline?
No, usually what happens, as I was discussing earlier as well, for the labeling piece, that you do not have, like, the central server is not having, or different sites are not having that access to all the sites when it comes to the format of the data, the quality of the data. But we can ensure with the help of some, let's say, packaging, for example, container, provide the container which is going to do validation before it allows to train the model. So do the validation of that particular data. If it satisfies the needs that we have already put into that kind of package solution, then only it will allow to train the model. But there is always a problem. Let's say image, an image dimension is, let's say, 100,000 cross 100,000 for the digital pathology. And when you are trying to train that model, what we will check at that point in time is the dimension. Like, are we training on 1D data, or 2D data, or 3D data, right? 2D black and white image, 3D, let's say, color image. And we can check the dimensions. That's what we can do. And on top of that, if we add a little bit of context from the subject matter expert, for example, in histopathology, most of the time, 50 to 60% of the time, you will see skin, which is a normal, and there might be some anomalies afterwards. So we can do those pre-checks before we allow that data to be used by our models. But still, that is a problem. So you cannot validate everything. You can incorporate few rules and regulations in place.
Yeah, exactly. So next question is about startups and usage of federated learning in startups specifically. It seems to me as if federated learning is not really suited for early stage startups, as I can't imagine hospitals being willing to spend their time implementing the solutions or trusting that the data will really stay private with small companies. Do you think federated learning is currently only for enterprises?
As a matter of fact, I see most of the startups jumping in,
Mm-hmm.
because the good news is that you do not need to host data. Like, I mentioned, a lot of the frameworks right now are open source, and enterprise customers never prefer to go with usually not prefer to go with the open source without having some one providing the service. Someone should be managing those open source frameworks, because open source framework, it might have some bug, or there might be some update. Like, who's going to manage? Like, I'm going to be focusing on my business use case rather than solving the bug with that framework itself. So there are a lot of startups, to be honest, that are investing in this direction, because there is no, let's say, standard, like, use this particular application for your federated learning machine, federated learning workloads. So a lot of things are happening in that direction, and companies are preferring going with the startups because they're agile rather than creating in-house, which in-house it gets difficult in-house, because it's enterprise regulations in place. Yeah.
Yeah, feel you.
Yep.
The next question: how are hospitals rewarded for providing their data for federated learning? Are they getting paid?
And they cannot get paid. That's the trick. Like, it's a patient information. They don't own it. So mostly why not only hostels, but in the federated learning, why do they participate is a simple thing. They also want what we want. That is intelligence, like updating their models, making those models much better. So that's the mostly what you see when it comes to the agreement. Like, at the end, you share models with us as well. Yeah, rather than they're selling it. They cannot.
Yeah. I mean, it's also for their advantage, to be honest.
Yes. Yes.
Do you think that in the future hospitals, etc., have to provide federated learning access to their data similar to open banking?
I mean, like, data is not gonna be, nobody's gonna make data available.
Yeah.
Maybe the models,
Mm-hmm.
trained models with proper regulations in place and proper constraints in place, but they're not gonna share the data. Not gonna happen.
Yeah. Okay, these were the questions that we had for our very first business talk in our deep dive days. Thank you very much, Munir, for joining today to us and giving us some insights about federated learning and MLOps. So yes, thank you very much for your time.
Thank you so much, Aiken, and thank you so much for the whole TUM.ai team for having me here and organizing this great Makeathon. May the AI be with all the makers.
Hopefully,
Yeah.
let's see. Okay,
Yeah.
amazing, Munir.
Have a nice evening,
You
everybody.
too. Bye
Goodbye.
bye. So everyone, we will jump into a quick break, but before jumping in, I wanted to share with you the upcoming talk, which is also extremely cool, and you should definitely watch it. So, first of all, today we will also host experts from Siemens Healthineers. It will start in 15 minutes, and I will introduce the experts later on. Tomorrow we will have a talk from Infineon and Roche, and on Thursday we will have a talk with Infusion. Later on we will host a partners lunch, and that's an amazing event if you want to network with all of these companies and experts, challenge setters, and also get to know us, the TUM.ai members. And on Friday, after the Makeathon kickoff, we will host a talk from Deloitte. So make sure to mark your calendar and block all of these places. And then we will have a Makeathon kickoff show on the 22nd at 10 a.m. And make sure to watch this one, because we will also give some insights about the Makeathon that you will need. And then the making phase will start officially. And on Sunday, you will need to submit your project, prototype, and business plan at 11 a.m. Then the track jury will happen, and then the finals, and we will know who will win the amazing prizes. And another news that I want to share with you is our recruitment phase is open right now. You can scan this QR code in order to land into our amazing website. We know that it's amazing. That's really amazing. And don't forget to join. Don't forget to fill out the form if you want to join us. And we are waiting for your applications. Then we will have a really quick break until 8:20. Then we will continue with the Siemens Healthineers talk. Till then, see you. Siemens Healthineers team. Today, the first talk will be hosted by them, and we are extremely happy to host this talk with Siemens Healthineers. So just quick info about today's speakers. One of them is Mediyar Hashemi. He's a product manager for AI solutions, advanced therapies in Siemens Healthineers. And our other speaker is Eric Alvarez. He's a research scientist in artificial intelligence. And today they will talk about cardiovascular care in sense of AI solutions. They will first examine the use case from a business perspective and discuss the technology and infrastructure afterwards. And I heard that the presentation is also supported by exciting videos and impressive pictures. So I'm looking forward to your presentation. And among other things, they will also show a digital twin of the heart. So I'm extremely excited to hear this talk. And I want to leave the stage to you. You can start sharing your screen.
Thank you for the introduction. So let me share my screen. Years, we believe in people. People are at the center of everything we do. That is why we are committed to pioneering breakthrough innovations in healthcare for everyone, everywhere. That means we want to push the boundaries of what is possible in healthcare to improve people's lives, the lives of all people around the globe. And with artificial intelligence, this is now possible. So who are we? We are the market leader in most of our businesses. We got 66,000 people in many countries. We collaborate with a lot of leading hospitals. And what all these numbers mean in the end is we can make a difference. And when we say we want to pioneer breakthroughs in healthcare for everyone, everywhere, we mean what we say, and we can do that. And digital data and artificial intelligence will help to make that possible. So what made me work in healthcare is that all these technologies, all these innovations, all these collaborations can really make a difference to people. It can really save lives, whether it's cardiovascular diseases, neurovascular, or cancer. It is making a difference. So let me tell you how all this comes live. Patient twinning. One super exciting example for CT diagnostic imaging. One that doctors are crazy about because it's so good. It's called NeoTOM Alpha. It makes super sharp images of the patient where you can see so much more. It's almost twinning the patient. The point is, the more you see, the more you can do. Precision therapy. When it comes to therapy, millimeters can decide between life and death. And guess who can be more precise? A cardiologist or a cardiologist with a robot? If your answer is the second, you're right. The robot's name is CorePath GRX. It's like science fiction. It can support to open the narrowed areas of the blood vessels in the heart. Exactly, to improve patients' life. And all these technologies, they do have one thing in common. Artificial intelligence to really make breakthroughs happen. Artificial intelligence can help improve decision making, and decisions are of different complexity. Let's have a look at some further examples how AI can help. When it comes to radiology, when it comes to CT imaging, the positioning of the patient is important. In 95% of all examinations, the patient is positioned wrong. On average, we are talking here about only 2.6 centimeters, but this has an impact. It leads to worse images. With artificial intelligence integrated in a smart camera, we can now make sure that the patient is positioned right for higher quality images, for better decision-making, and for better diagnosis. Time pressure. Time pressure has been and will most probably always be a challenge in healthcare. Staying with radiologists, we are facing today already an error rate of 30% for radiological examinations, 3 out of 10. Studies show that when the demand for reading images increases, the error rate will continue to increase significantly. Let's now see which difference AI can make. Here an example for CT lung scans, the lung of a patient who has suffered COVID-19. AI helps here to measure the impact of the COVID-19 disease on the lung. It automatically detects and quantifies the extent of the total COVID-19 abnormalities based on 3D segmentation of lesions, lung, and lobes. When it comes to cancer treatment, whether it's lung, breast, abdominal, or brain cancer, the planning part is very important. With the help of AI algorithms, trained on 5.5 million datasets, it automatically segments 71 organs at risk for the radiation therapy. After all, we only want to treat diseased organs and tissue while leaving out healthy ones. Coming to heart diseases, 40% of people in Germany die because of cardiovascular diseases. Now imagine we could create a digital twin of the heart, a digital copy of the patient's heart, a digital copy that works virtually like the real heart, so that the physician could test out different treatment strategies, options, to identify the best one for the patient. Imagine what possibilities this could bring. Imagine how many lives it could save. So when we are innovating, developing new technologies, we don't just do it in a black box. We are doing it in constant collaboration with physicians around the globe. So when we ask them, can this help you? The response was through the roof. They were like, yes, they see the value. Yes, they see that it can make a difference. And yes, they see that it can save lives. And this is how artificial intelligence and digital twinning can help you live longer and healthier lives. And now, handing over to Eric, he will tell you how this stuff works.
Thank you, Medier. So I'm going to start with showing how does the modeling of the digital twin of the heart work. So what do we need basically to create a model of the heart's patient? The short answer is patient data and biophysics. The heart is a complex organ which has 3 types of biophysical problems involved, from electrophysiology to biomechanics to the circulation of the blood inside the chambers. Moreover, it is a multi-scale problem because it goes from cellular to the organ level. So in order to have a patient-specific heart of the patient, first, we need to personalize the anatomy of the patient. For this, we need images, medical images, such as MRI, CTs, or echocardiographies. And then from these images, we need to perform a segmentation and generate the anatomy that will reflect the shape of the patient's heart. Then we need to personalize the electrophysiology, which is the part that describes basically using biophysics, which is the propagation of the electrical wave in the heart, as you can see in the small video. For this, we typically use data that is acquired in the clinical routine, such as 12-lead electrocardiograms, which is non-invasive data, or electroanatomical mappings, which are more complicated to acquire using catheters inside the ventricles. Then, once the heart is activated, once each of the cells is activated, they start the contraction procedure, following the biomechanical of the heart, in which the heart is contracting and dilating. Finally, this contraction dilation makes that the heart is pumping blood throughout the entire body, which can be simulated thanks to computational fluid dynamics. So as you see, it's a very complex problem. I will start showing how we personalize and how we leverage AI to make the patient-specific anatomy. So first of all, we have an AI-based image segmentation algorithm, which segments the ventricles and the atria, basically all the chambers of the heart. And then from this segmentation of the atria and the ventricles, we can perform a volume mesh generation. This mesh is important because it's a lot of tiny tetrahedrons or triangles in which where biophysical equations that I presented in the slide before will be solved. Then our AI algorithm also automatically does the tagging of different regions of the heart, such as the left ventricle, the right ventricle, or the myocardium. And these tagging regions are used later on to personalize each of the specific parts of the heart. Afterwards, we generate also the fiber orientation, which is crucial for the simulation of the electrical propagation towards the heart and also the direction in which the heart is contracting. Moreover, when using the images, the MRI images, we can actually identify the scar regions for the patients who have scars within the heart, which provides us information on the anatomical model that will tell us which parts of the heart are getting conducted slower. So another question is how to leverage modeling for cardiac electrophysiology. We have several phenomenological and ionic models of the heart. This basically means that we model using partial differential equations the relation between the different ions inside and outside of the cell. As you can see in this small scheme, basically we model the relation of the potassium and the calcium going in and outside of the cell. And in order to solve these equations, we basically use numerical methods, which consist on solving approximate solutions of the equations that tells us how the heart is going to be, how the electrophysiology is going to propagate through the heart. For this, we use state-of-the-art methods such as the lattice-Boltzmann method, because it allows the computation of a heartbeat in less than 3 seconds, and it's allowed to be parallelized using our computational cluster at Siemens Healthineers, which makes us being able to run tens of thousands of simulations a day. Another very advanced way of solving the electrophysiology of the heart is by using a graph-based approximation. This is useful for non-complex arrhythmia, such as the ones of CRT, and it allows us to be even faster than 3 seconds and computing in faster than real time, so solving the solution of 1 second per heartbeat at only 100 milliseconds. At the end, we have an extremely fast solution of the cardiac electrophysiology using AI and modeling, and then we can basically generate the virtual electrocardiograms, as you can see here, by generating a new model of the torso potential, in which the electrophysiology that we compute on the heart is propagated to the torso of the patient. And then at each of the different leads, we can generate the signal, the virtual ECG signal. Why is that important? Basically, because we want to have a model that is patient-specific with as little data as possible. So ideally with using non-invasive data, which means data in which you don't need to enter into the body in order to be acquired. For example, 12-lead ECG. This is commonly performed by placing the different leads on the patient's body. And if we compare our virtual ECG of the digital twin of the heart of the patient against the observed ECG of the clinics, as the one you can see on the screen, we can basically optimize the conductivity of the different parts of the heart in order for different key performance indicator for different KPIs to be matched, such as, for example, the QRS duration, which is the duration of the longest part of the ECG, or the electrical axis, which tells you in which direction the electrical propagation is going. We do that by using a data-driven regression model. So it's machine learning. And here you can see in one of the papers of media in which basically we tried to match the observed ECG that you can see in the background with the virtual ECG of our personalized model. Another thing that we can do after we work with non-invasive data is go further and try to get more useful data, such as the invasive data that we can get in the clinics, the so-called electroanatomical mapping. This is the common procedure when treating arrhythmias, in which we get several points within the ventricles. So the question there is, can we estimate myocardial activation times from these SPAR measurements? Because in the clinics, we usually get several measurements within the endocardium, but we don't have any information of the myocardium or the epicardium. Therefore, we basically used a neural network architecture to extract local features and global features in order to predict local activation times. And in this paper of 2021, we showed an accurate reconstruction of endocardial activation times, as you can see here. The more samples we give, the closer we are to the ground truth. And we showed as well that it's much faster than personalized computational model. So now I showed what's the thing. So how can we personalize a model of the heart using patient data? And as Mediar said, the advantage of having a virtual representation of the heart's patients is that we can, first of all, simulate diseases and also test treatments virtually. So what I'm going to tell you next is I'm going to show you the different arrhythmias in which we work as applications of the virtual heart. As you can see here, those are the most common arrhythmias: the atrial fibrillation, the ventricular tachycardia, and the desynchrony. So first of all, I will start showing you the atrial fibrillation because it has a high societal burden. It affects 2 to 3% of the population, which means, translated into money, more than $26 billion alone in the US. And moreover, this disease is not treated once. So once it is treated performing ablation, the patient usually needs to come back. About 30 to 50% of the patients need to come back and do another operation, which means that several people with AF cannot, for example, run football, like go for football or for extreme sports, and therefore they get an operation, they don't get treated, and they need to come again. So the idea is to use the digital twin to test several treatments, such as several different locations of the ablation procedure, and see which one would be the best before going into clinics. So here you can see an example of one of our demos within Siemens Healthineers for the simulation of arrhythmia, in particular for the simulation of atrial fibrillation. We did that on 56 atrial fibrillation patients, which was up to date the highest cohort of atrial fibrillation patients existing. And moving forward to the next application, another application which is commonly used in the clinics is the application of a cardiac resynchronization therapy. So basically about 150,000 patients per year get cardiac resynchronization therapy, which is commonly known as well as pacemaker. So a lot of people having heart failure, having difficulties to breathe, to do sports again, need to have a resynchronization of the cardiac chambers so that the heart keeps pumping. And about 30 to 50% of these patients do not respond to therapy and need to have another operation as well, similarly to with the problem of atrial fibrillation, which means a total of $37 billion in the US. So what would be the application of the digital twin of the heart in that case? It would be to basically optimize the placement of like the location of the pacemaker and the timing at which the pacemaker is activated. For this, we showed an application in real life. So we went to Bordeaux in France. We focused on cardiac resynchronization therapy. And on the first day before the intervention, we personalized the anatomy of the patient. We generate the chambers of the ventricles. And then we use the ECG before the operation was done to personalize the cardiac model. During the intervention, the digital twin was updated with interventional measurements, such as the ECG and the sense delay, which means the time at which each of the leads is getting activated in the cardiac resynchronization therapy. And we saw that it was able to predict accurately the outcome of the procedure in real time. So it was here in the clinics, you can see some picture, and the model was doing in a similar pattern the prediction of the QRS reduction. So this is pretty impressive, and it's very nice to see powerful, like how powerful our digital twin of the heart can be. Let me show now an example, real life example. This is a demo. Afterwards, if you have questions, we can go to some of the different applications that we have here. But now I will just go to the main one and explain you the others. The first two are applications of the creation of the anatomy of the heart. So you can see here, the Echo Builder is basically using echography pictures, and the MRI Builder is using magnetic resonance images to build the geometry of the heart using our deep learning algorithm for segmentation. The Heart Builder is the one that consists on generating all these steps that I mentioned before on the anatomy. So it generates the fibers, it generates the tagging of the different parts of the heart. It generates also the scar information if the patient has scar. And then we have everything ready to start simulating the patient. So now I will show you an example of a simulated patient. First of all, let's check at the segmentation that I mentioned before, which can be seen on this application of the cardiac resynchronization therapy planner. Here on the left side, you see the medical images of this patient. On a short axis, on the 3 chambers, on the 4-chamber view, where you can see the different chambers like the 2 ventricles and the atria. And you can as well see the segmentation of our deep learning algorithm. And you can see that for each of the different images, and also the resulting volume mesh. So this is the volumetric mesh with the different taggings for the inner part of the ventricles, for the outer parts, and so on. You can also decide what to observe, what not to observe. Then what I wanted to show is once this is ready and you have the entire anatomy of the model, you can perform a simulation, and the simulation will give you basically the potential, so the activation and the deactivation of the heart chambers. And it will also give you the ECG, the virtual ECG, in which you can see here basically one of the leads only for reference. One very important thing is that for this patient, we performed personalization. So you can click here and personalize to the measured data. So this patient had a QRS duration of 140 milliseconds, QT duration of 428. And we changed the different conductivities within the heart using our AI algorithm for personalization. And we obtained the following computational values. And those are the most important KPIs, the first 3. So the idea is to match the QRS and QT duration as good as possible in order to have the virtual heart of the patient in the computer. Then once this is done, we have the personalized patient of the patient, and this patient has 140 milliseconds of QRS duration, which is a long QRS duration. So this patient has a disease, In fact, if we go back to the previous component and we take a look at the depolarization time, which means the activation times, we see that this patient has red means the initial activation and blue means the last one. So the activation starts from the septal wall and it goes up to the left ventricle, which is that one. And as you can see, the left ventricle is much greener, so it gets activated much before the right ventricle. So this patient has what is called a left bundle branch block, which is LBBB, which means that the right ventricle is activated much before the left ventricle. And this, in reality, means that this patient cannot do sports, will have an ejection fraction, a very low ejection fraction, and needs to have the heart resynchronized because this, the left and the right ventricle should be at the same time beating, right? It should be synchronous. So what can we do to do that, to solve that? We can perform what is called a cardiac resynchronization therapy. This means, in reality, this patient goes into operation room and they put a catheter inside and they put a pacemaker, right? And they decide where to place it. In our case, it's much easier. We can decide where to place the different leads of the patient. For example, on the right ventricle, it's typically placed on the septum, and on the left ventricle, it can be anywhere. We can choose those places because those places were the ones chosen for this patient. In particular, it was close to the septal wall for the right ventricle and a bit more to the left than this point for the left ventricle. And then we can perform a simulation. Since the model is already personalized, you will see that the simulation runs extremely fast. Before we perform the simulation, we can decide if to activate one of the leads on the left ventricle or two of the leads. So in the clinics, they did that as well. They activated first only the left ventricle lead, which you can see soon. And as you can see now, the activation of the heart starts from the left ventricle, while on the right ventricle, it has not been activated. It's just the physiological activation that we saw before. And they observed that the QRS duration was reduced, but very slightly. So this patient could still not perform sports, and it was not the optimal treatment, right? So what did they do? They tested for biventricular, like basically activating both of the leads at the same time. And they observed, in fact, that activating both at the same time, they achieved a much more synchronous pace. And they reduced the QRS duration to 96 milliseconds, which is a much healthier heart response, right? So thanks to this, they could perform, the patient after the operation room could hopefully run much better. The last thing that I want to show you basically is, so here you have the ventricle, the two ventricles, here again, the ECG, right? And here you can see the depolarization map. And another thing we can do is, since the simulations are extremely fast, we can perform different positions and check which of them is the most optimal position, right? So now the computer is computing all the different positions and checking which is the placement that is most optimal for a QRS reduction. And in fact, it is exactly the 11, the one that I showed that the clinicians used as the best one. But how good it would be if we could perform all these simulations before operating the patient, right? And knowing already which is the best placement. It would save an extreme amount of time and an extreme amount of money. And now let's go back to the presentation in which I will show how we in Siemens Healthineers think about the future of healthcare. Oh. Can you hear the video?
In the decades ahead, healthcare will undergo dramatic transformations. Medicine will become more precise. Value will shape care delivery. Patients will become empowered consumers. And digitalization will transform every facet of healthcare. Patients will have a digital twin, a customized computational model of themselves, enabling Dr. Clive to anticipate illness, guide therapy options, and predict outcomes of procedures. Expanding precision medicine will enable radiologists to make highly specific diagnoses for Stephen without unwarranted variations. AI-powered decision models, fed by vast population health data, will improve diagnostic accuracy. Healthcare will become anticipatory, organized around Paula's medical conditions, and available around the clock, transforming care delivery. Multidisciplinary, highly productive care teams structured around patients and their needs will collaboratively deliver the full cycle of care. All interactions with John will become convenient, personalized, and compassionate, improving patient experience. Supported by real-time monitoring and guidance, John will become more empowered and have physical and virtual access to care when and where he needs it. At Siemens Healthineers, our mission is clear. We pioneer breakthroughs in healthcare for everyone, everywhere.
So to end up, I would go back to the first question that Meteor raised, and it's whether AI and digital twin will help you and all of us live longer and healthy lives. And yes, we at Siemens Healthineers believe that AI and digital twin will make it happen. Thank you, everyone. Feel free to reach us out for any questions, but for now, Meteor and I are happy to answer the questions.
Amazing. Thank you very much, Erik and Meteor, for this amazing presentation. And of course, we have a lot of questions for you. So we will start with the first one. It's about Watson Health and what you're doing differently from them. Watson Health was supposed to bring AI into hospitals, but despite billions in funding, what has changed, or what are you doing different so that you are succeeding? Stage is yours.
Can you repeat the question for a moment? Sorry.
Yes. No worries. Watson Health was supposed to bring AI into hospitals, but failed despite billions in fundings. What has changed, or what are you doing different so that you are succeeding?
So what are you doing differently? Erik, do you have an answer for that? I mean, at the end, I guess what I also try to convey, somehow we are a purpose-driven company, right? We want to pioneer breakthrough innovations in healthcare. We want to push the limits of what is possible in healthcare to improve people's life. And for this, we do have 66,000 people around the globe. We work also very closely with clinicians, with physicians, with customers, to make sure that we drive technologies, that we drive research, that we drive or bring products to the market that really address a clinical pain point and help physicians to treat their patients at the end, to improve patients' lives and to save lives. I guess a strong purpose-driven company plus strong focus on value, on clinical value, on customer value, and then finally, 66,000 people having a strong focus on it. Mm-hmm. Erik, feel free to add something if I missed something.
Yeah, no. It's a very good answer. It's difficult to know why the others failed, but we can answer, as Meteor said, what we are doing to try to do our best, right? With 66,000 people is a lot of people working on that. and our purpose is clear, and we work really close to physicians. We work a lot with clinicians, even at the research level, right? They are very interested. We work in the hospitals with hospital data, and these collaborations are helping us a lot not to do mistakes and to do what they are most interested at as well.
Amazing. Then the second question is about classification models. I heard that it's easy to build a working classification model based on X-ray or CT scans for one hospital, but as soon as you try to apply this to patients at a different hospital, it fails. Did you see this in practice? If yes, how do you deal with that?
Yeah, that's a very good question. I would say it not only depends on the hospital, but it also depends on how the data was acquired, right? Which manufacturer, because it's not the same acquiring it with Siemens Healthineers or another manufacturer. So in general, if it's acquired with the same machine, it shouldn't be a problem. If it's not acquired with the same machine, but it's the same kind of data, it shouldn't be a problem either with the latest algorithms that we have. So we have tested it on different data from different manufacturers, even for contrasted CT and non-contrasted CT. And we have some segmentation algorithms that work with contrasted CT definitely, and with non-contrast CT as well. Which non-contrast CT, you don't see very clearly the chambers of the heart, right? So it's relatively independent on the vendor.
Yeah.
But a good
Makes
question.
Sense. Yeah. And the other question, in computer vision, we often have the case that models perform better for light-skinned subjects. Do you think that this will be even more pronounced in healthcare? For example, predictions for average-sized people will be correct but fail for obese ones.
There is I would answer with this. We have observed, right? There is definitely a bias. Also because of the amount of data that we have on the different, like there is in comparison with the percentage of people that is obese, except for maybe heart problems, for other problems, there are more people that are not obese, right? So we are biased towards that kind of people. But of course, we are working to reduce that bias and being able to have the same accuracy for obese people.
Yeah, bias problem is everywhere.
Yes.
Amazing. The next question is about the digital twins. I have experience in AI, but never worked with digital twins. Is there a standard first Hello World problem like the MNIST for digital twins? Something easy with good documentation to get started.
That's a tricky one. There is, it depends on the level of precision of the digital twin. So for example, the ones on the companies are not commercially available. The one that I know that is, they are not open source, but the one that I know that is open source and is nice to start playing with is a 1D model, right? So it's not like the 3D model that we are seeing here in Siemens Healthineers, but it's 1D, but it's also very useful for a lot of clinical problems. And it's called CircAdapt. It's from Maastricht University.
Oh, okay.
So that's a good start if you want to play with the digital twins. They also did a lot of research on AI combining with their models. Yeah.
Amazing. We can check that out.
Yeah.
Is the virtual health already used in practice, or is it still in the research state? If still in research, what does the time horizon look like?
So the digital twin of the heart so far is a research topic. And for sure, we won't make any commitments with regard to when we will make it to the market. So we do have amazing collaborations with amazing physicians around the globe. As Eric shared with you on CRT interventions, on atrial fibrillation. So really specific on concrete diseases, trying to make a difference, figuring out which challenges we need to overcome. when it comes, for example, to acquiring the data, standardization is an important topic. Yeah, there are people working on this topic, and let's see how it continues. But I can tell you, it looks quite promising at the moment.
Fingers crossed. The next question is about the countries, actually. Do you see a big difference in the uptake of these new methods based on the countries you're operating in? For example, is Germany rather conservative in adapting these solutions than the others?
For sure. Looking at the world, the countries, the continents do have different requirements. That's why also in general, when it comes to introducing or bringing new products to the market, new technologies, new innovations, somehow we want to make sure that we deliver scalable solutions that can be
idea?
Yes.
Okay.
Okay. If you want to add something, Eric, you can maybe jump in until he arrives here. If not, we can just skip to the next question, which I know that you're the person to ask to. Fluid simulations, electrodes, etc. Makes me think that as a more classic computer scientist, I'm lacking the knowledge to build AI solutions for this area. Or am I wrong? And these are things that could be learned on the job while doing it.
I think definitely you can learn that. I mean, it's always good to have like mechanical simulation background, mathematical background, or physics background. But every day, more and more, more or less since NeurIPS 2018, as you probably know, there is like a current trend on AI for simulations, right? So you still need to know the maths behind it. It's nice. But if you know a lot about AI, you can also kind of skip a bit of maths, I guess.
Yeah.
So you can learn it, definitely.
Yeah. Another question about the demo that you showed. In the detailed heart demo that you showed, there was a small tube that always stayed violet blue. Was this part just not simulated, or is there another reason?
Yeah, very good, very well observed. That's the part of the corresponding to the atria and the aorta. So we don't simulate that part. We simulate the rest of the part for the electrophysiology. Yeah.
Is there a reason for that? Reason?
Yes. The reason is that we observed that when simulating only the ventricles, we are doing that for ventricular applications, right? So for CRT and also for VT, we are simulating only the ventricles. This allows us to save computational time, but also we observe that it's not necessary to model that part of the and as well, this is the part of the segmentation that usually creates more problems because it's difficult to identify the veins and the arteries going out of the heart, right? It's in comparison to segmenting the entire cardiac chambers.
Yeah.
That's the reason.
Hello back, Mehdi.
Yeah, look like that. I'm somehow here facing some Wi-Fi challenges, but let's see whether it works now.
Okay, amazing. The next question is about precision medicine. Precision medicine sounds great, but also so futuristic when considering how long basic digitalization is taking. Do you think that private healthcare will be way quicker to adapt such solutions, and this will lead to a big gap in the quality of care?
You want to answer, Media?
Still thinking about the question. So can you?
I can repeat it.
In a nutshell.
So the digitalization, like basic digitalization, even we use in daily life, especially in Germany, takes a lot of time. Do you think that private healthcare will be way quicker to adapt such solutions like digital healthcare and etc., like futuristic solutions that you mentioned and also showed in the video, and this will lead to a big gap in the quality of care? So the adoption time of the healthcare solutions, what do you think about it? Is it going to be way quicker in comparison to other things, or is it going to be the same? Is it going to be tricky?
Thanks. Yeah, great. So you're right. So the adaptation times will be different, looking at different geographies, whether it's a public or private hospital, whether it belongs to an integrated delivery network like in the US, where do you have a big hospital chains. For sure, there will be differences when it comes to digitalization, when it comes to preventive medicine or personalized medicine, when it comes to digital twinning or artificial intelligence. But I would rather not just somehow link it to whether it's a public or private hospital. I guess it's more a question of the individual hospital inside and country, how quickly and how enthusiastic they are regarding digital data and artificial intelligence.
Amazing, makes sense. Yeah. I think we are over the questions for today. Thank you very much for your time and for that amazing speech. We all got inspired, and we are also looking forward to meeting with you if you have time in Partners Lunch on Thursday. So thank you very much again for your time today, and hope to see you in Partners Lunch.
Thank you very much for the invitation.
Thank you for having us, and I wish you exciting days, amazing developments, and yeah.
Thank you very much. Okay, everyone. So we will continue again with our upcoming days. So as we mentioned before, we have some more expert talks from companies such as Infineon, Roche, Infusion, and Deloitte. So make sure that you mark those days in your calendar, because the experts are incredibly amazing. So you shouldn't miss that. And again, with the QR code that you see on the right side, you are going to land into our application platform. If you want to be part of the TUM.ai community, which is an amazing community, and you will get to know many of us in Partners Lunch. So if you want to be a part of the community, don't forget to apply, and we would love to see you in our community. So this is the end of today's Deep Dive Day session. We hope that you enjoyed it and hope to see you tomorrow in the next talk with Infineon and Roche. Have a great night.